So let's take a look at how you can use software-defined radio profiles to deploy dual 5 GHz deployments and how to configure and use dual 5 GHz access points. The environments where this is going to be necessary will be high-density environments. So let's return to the example that we used in the Wi-Fi fundamentals section of this course. And we will take a look at that multi-room, multi-classroom design scenario. And on the screen, you see the coverage and the radios of both 5 GHz and 2.4 GHz radios. And in this case, these are static dual band access points. One radio serving 2.4, the other radio serving 5 GHz. On the 5 GHz, so you'll notice we have one AP per room design. In the 5 GHz range, each classroom or each room has its own AP and one channel, one radio on 5 GHz available. On 2.4, because we wanted to reduce the amount of CCI or co-channel interference, you see that only a couple of rooms, or 1/3 of the rooms roughly, have a 2.4 radio turned on. And we said that in such a scenario, in one AP per room, in this case, we figured out that only 1/3 of the 2.4 radios needs to be turned on in order to A, provide coverage, and B, avoid CCI or co-channel interference, or at least not avoid it completely, but mitigate it as much as possible. Now, that means we're throwing away 2/3 of all the radios in the access points. And we're not using any of those radios. So wouldn't it be better if we had an alternative where we could use those radios since they're already there? And the alternative is called dual 5 GHz access points. And you can configure dual 5 GHz access points in two ways. You can statically select which frequency band the Wi-Fi 0 interface is going to operate in, or you can let an SDR profile tell the ACSP protocol and let the ACSP protocol decide which frequency band does the radio need to be on. So in the case that you have in front of you, you could say, okay, let's turn all the 2.4 Wi-Fi 0 radios into a SDR enabled mode, and then the ACSP algorithm would figure out which of the radios need to be on 2.4, which need to be on 5 GHz, in order to mitigate CCI and provide the best possible capacity at the same time, thus protecting your investment, and you're not throwing away any of the resources that you have. And in some cases, you might actually reduce the amount of access points required for this deployment just by implementing the dual 5 GHz channel scheme. When we were talking about 5 GHz frequency band and we spoke about the OFDM spectral mask, we said that the two neighboring 5 GHz channels actually do overlap slightly. And now, since we have two 5 GHz radios within the same physical AP, we run into that constraint. So we do have some overlap. There's two things that Extreme Wireless Cloud APs do to mitigate that. One is they provide a 60 decibel isolation between the two radios so that we mitigate that issue. Otherwise, you'd be running into a similar problem like co-hosting or co-locating two access points in the same physical space, which would still cause interference. So that's mitigated by also implementing a 3 times the channel bandwidth frequency separation. So there's going to be at least 60 megahertz separation between the two channels if you're using the 20 megahertz channel scheme. You will need to have much more separation, namely 120 megahertz if you're using 40 megahertz channels, and do not use 80 or 160 megahertz channels whenever you're deploying dual 5 gigahertz. It just won't work because you won't have enough channels to reuse. You will need to enable DFS channels, so you have enough channels to be able to use to provide non-overlapping channel deployment. And the rules that you see on the screen are actually already implemented in the ACSP algorithm. So the ACSP algorithm will actually figure this out for you. So this is just for you to be aware if you're doing a manual or a static channel selection. But the ACSP algorithm will actually adhere to these rules and implement it the way that is the best for this environment and the best for the dual 5 GHz solution to work. So the ACSP will again use the cost-based algorithm to select the best channels, and the preferred channels are going to be the ones that are non-DFS. So in this case, Uni 1 and Uni 3 in the example that you see on the screen. It will implement a 60 megahertz separation if you're using 20 megahertz channels. It will try to also then bond a non-DFS channel with a DFS channel, just in case you have radar blast, so that the only one of the channels on the physical AP is affected. And when you're designing, while you can use 40 megahertz, we said that you need 120 megahertz separation between the two channels on that same AP. So you can use 40 megahertz, but please note that it needs more separation and it's more rigid in terms of the design. So whenever you can, please use DFS channels with 20 megahertz bandwidth whenever possible. So the SDR profile will basically tell the AP two things. Which radio profile to use when it is in 2.4 gigahertz mode, and which radio profile to use in 5 gigahertz mode. And also, you will tell the AP when to do the frequency band switching. So when to switch from one to the other. And all of these settings go back to an algorithm called ACSP. So we already saw when the AP boots up, it goes into an ACSP process to determine the best channel and power selection. When you have a dual 5 GHz AP with SDR profiles enabled, you add another step to that process, and that is, okay, let's determine which channels should be assigned to 2.4 and or 5 GHz, and then it will decide which frequency band to use. So if you look at the flow diagram, you start the ACSP process, make sure you have all the information on all the channels, then start the SDR process and detect which frequency band to use, and depending on the threshold meaning amount of interference, amount of CCI, you either stay on 2.4 or assign a 5 GHz profile to this radio. Make sure you have enough channel separation, implement the channel and power selection that was determined by the ACSP, and you're done. And on 2.4, same thing, you don't apply 5 GHz, but you do implement the power and channel selection that was determined by the ACSP protocol. So this happens on boot. And then this same thing can run periodically depending on how you configure your SDR profiles. So your ACSP is already configured, like we saw in the lab, to dynamically assign channel and power, depending either on a specific time or day or during a specific time window. And you can do the same thing for the SDR profile. So you can implement the same decision making. You can basically short circuit this process during specific times of day and only have it running up at night, for example. So the good practice would be measure throughout the day and implement changes when they're least disruptive to clients. So normally we see ACSP and SDR deployed in a way where the changes to the channel and power and the frequency band would be implemented during the night based on the measurements that happen during the day. This would be the least disruptive way of implementing this without disrupting any client connectivity, without causing any dynamic or domino effect changes in your network during the day. But then again, it depends on your network design, it depends on your network requirements, and it also depends on the environment you're running this deployment in. But the combination of ACSP and software-defined radio profiles gives you all the flexibility you need to be able to deploy high-density networks and also to adapt to this highly changing or ever-changing IF environment.